Alright, so we've been talking about latitude and longitude, and that's all well and good, but it's time to get things a little bit more interesting. Okay, so one point I want to make straight up is that latitude and longitude is a coordinate system. It is not a map projection. We're going to define map projections near the end of this video tutorial, or the next one in the series. But there's a difference. Okay, latitude, longitude, this is in degrees, minutes, seconds. It is different than a map projection. A map projection is used to take three-dimensional data and present it in a two-dimensional way. Okay? Latitude and longitude is not doing that. It's a coordinate system. It tells you where you are in space. Okay? It's just a question for you to sort of think about with latitude and longitude. So if you, for whatever reason, you were lazy, you had one leg, whatever, you wanted to cover the least amount of distance and you wanted to travel around the Earth, which option would you choose? And I'll let you guys think about that. Okay. Mapping the world. Let's get things a little bit more interesting. Let's think about actually mapping the world and how we can do that. It's a little bit more difficult than you might imagine. The Earth is not a perfect sphere. The Earth is an oblate ellipsoid, or an oblate spheroid, which is slightly ridiculous, but that is what it is. It is this very complicated surface, right? Because of plate tectonics, because of erosion, because of interplanetary history, there's all sorts of complicated things happening at the Earth's surface. And we are doing our best to try to accurately portray it somehow. And one way we can do it is using something called an ellipsoid, right? You don't need to memorize any of these equations, but this is an ellipsoid. It's a mathematical construct. It's a mathematical model where we've got these different axes of different sizes. We can use them to create this ellipsoid. This black, in this call out, this black line here is this regular ellipsoid. Here's the irregular Earth surface, right, with mountains, topography. It's fantastic. This is the ellipsoid, and this blue line is something called the geoid, which we'll define in just a little bit. We have different ellipsoids that we use in mapping. This is an example of just three of them. The Clark 1866 spheroid or ellipsoid. Those terms are interchangeable. WGS 84 spheroid or ellipsoid. We can see that they're different from one another by the distances of their semi-major and semi-minor axes. Okay, so these guys are different. These guys are different. These guys are the same in the semi-major, but they're slightly ever so different in the semi-minor axis. Okay. Well, why do you think we have different ellipsoids? Why can't we just have one? One ellipsoid? That's great. But no, we've got just many, many ellipsoids. Why would we, as map people, do that? Well, this is what we're going to try to answer in the next sort of thoughts. And to do that, we're going to help to define something called the geoid, which I already just talked about. But again, the ellipsoid is this mathematically defined regular surface. The geoid is the surface the oceans would conform to if free to adjust to, I'm just reading this, right? Free to adjust to the combined effect of gravitation and the centrifugal force of the Earth's rotation. Essentially what this means is the geoid is the surface the oceans would relax to if they were able to just sort of, float underneath the land and just sort of do their thing. If they're able to just relax under gravity and the centrifugal force of the Earth's rotation, the geoid is the surface that they would conform to. And the geoid is closer, it's often closer to what the actual Earth's surface is than the ellipsoid alone. But because of plate tectonics, because of the history of erosion, because of all this fascinating things having to do with physical geography and climate change and patterns and all these different things, the Earth's mass is unevenly distributed, right? We've got places where mountain building is occurring. We've got places where we've got deep, deep trenches. Okay, we've got different types of crust, all these really fascinating things. And because of that, there's around the world a difference in the difference between the ellipsoid and the geoid. And I have some graphics here which will hopefully make this more clear. This particular guy works really well for North America. But other ones don't work very well for North America, and we're going to see that. We're going to see that here. So this is an example. We've got our geoid, which is this thick black line, and then we've got our ellipsoid. Okay. Let's say that we're really interested in mapping North America. Okay, that's our area of interest. This Well, so the best ellipsoid we could choose to map North America, which would match the geoid very well, would be this blue guy, right? Because, let me take him away. Oh, go away, blue guy. Okay, bring in the blue guy. That looks awesome because it's matching up really nicely with the geoid. This red guy is doing this red guy is doing a terrible job of mapping up North America, but this red guy is doing a beautiful job matching up the geoid around Europe. Whereas the blue guy is doing a terrible job in Europe, nice job in North America, horrible job in Africa, right? And so this is why we have different ellipsoids or spheroids, because of the distribution of mass around the world, which is unequal, different ellipsoids will do a different and better job in some places than others. There's a little graphic, and it's showing you the ocean surface, it's showing you the reference ellipsoid, which is that dashed green line, a local plumb line. So this is like a plumb bob. So if you have a weight on a string, you let it go. Which way is it going to fall? You think it would fall right at at the Earth. Okay, but if we've got a big landmass right here, and our plumb bob is up high enough, actually this weight is going to be swung a little bit towards the big mass because there's more mass and gravitational pull over here than there is over here. Okay, number 4 is actually showing the land surface, and then number 5 is the geoid. Let me just go back to this quickly. We can see that the surface of the Earth is still kind of different than this reference ellipsoid, right? So there's a problem, right? We've got this differences in the height here, and we need to do something about that. And can't we use our mathematical powers to figure that out? Well, we can. And what we use to help out our ellipsoid is something called a datum. A datum incorporates local variations in elevation, and it does a better job than the ellipsoid alone. So the datum, it's like a series of local corrections we add on top to the ellipsoid to incorporate these variations in elevation. So what we see here is, this is for Bellingham, Washington. These are the coordinates for Bellingham, Washington in decimal degrees. If we use this datum, NAD 27, versus this datum versus this datum. It's all the same place, right? It's not like the place is moving around, but we can see that if we look way out here in the long, small decimal places, we can see different values for these guys, okay? But it's the same place. It's because we're using different datums. These are different coordinate values, right? If we don't know what the datum is that we're using, and we make an assumption that it's, if we're actually using NAD 27, but we think we're using WGS 84, this can add up to, because they're different, hundreds of meters of offset. And this can become a real problem. There's over 240 geodetic datums in use. Okay? And if you don't know which one you're dealing with, you may be in trouble. If you're thinking about property lines, if you're thinking about military applications, if you're thinking about almost anything, you need to understand the datum. And this is where metadata comes in. And metadata is data about data. Metadata is sort of background information that you use. Because if you're just giving somebody, you say, okay, the location of this, treasure box of gold is at this latitude and this longitude, but you don't tell them what datum you're using, the person might be totally off, and they'll be very tired because they'll keep digging and they're not going to find that treasure trove. All right, I'm going to stop this video here, and then we're going to talk about map projections in the next one.